Welcome to Microelectronics 1A. I'm going to discuss the following topics: silicon semiconductor, doping of silicon semiconductor, that is N-type silicon, P-type silicon, MOS, transistor symbol and its terminals, operating regions of MOS transistor, that is the subthreshold region, linear region and saturation region. Silicon is a semiconductor. Its atomic number is 14. So it has 14 electrons. In the nucleus it has 14 protons and 14 neutrons. This is the Bohr's model of silicon. Here you can see the nucleus, which has 14 protons and 14 neutrons. The 14 electrons are distributed around the nucleus in shells or orbits. In shell 1 has 2 electrons, shell 2 has 8 electrons, and shell 3 has 4 electrons. So in the outermost orbit of silicon we have 4 electrons. These are called as valence electrons. So silicon has 4 valence electrons. Let us see how silicon material looks. A silicon atom is surrounded by 4 other silicon atoms, and each silicon atom will share an electron to the center silicon atom. Hence now the silicon atom here has 8 electrons on its outermost shell. This bonding is called as covalent bond. Doping. There are 2 types of doping, that is P-type doping and N-type doping. Arsenic is called as donor atom because in its outermost shell it has 5 electrons, that is in the shell 4. You can see in the Bohr's model 1, 2, 3, 4, 5. And boron is called as acceptor atom because it has its atomic number is 5. In the first shell there are 2 electrons, and in the third shell there are 3 electrons. Let's see why they are called as acceptor and donor atoms. So let us dope or add a foreign atom, that is an arsenic atom, to silicon material. So once we add an arsenic atom to the silicon material, an extra electron is generated. This extra electron is the charge carrier in this N-type doped silicon atom. The N's electrons are the majority charge carriers in N-type doped silicon atom. These electrons are free to move. So once this electron moves away from arsenic has 1 electron shortage. It has more protons than electrons, and it is, now we can call it as an arsenic positive ion, which is shown here. Coming to the acceptor doping, when you add an boron atom to silicon material, boron has 1 electron less, and hence a hole is created. Hole is nothing but a positive charge electron is created. So electrons can jump to this hole, and this is how the holes are the charge carriers in P-type doped silicon atom. Here we do not monitor the electron movement, instead we monitor hole movement, hence holes are the majority charge carriers. Once an electron falls onto this hole, a new hole is created here. Now boron has more electrons than protons, and the boron becomes a negative ion. This is the bird's view of a MOS transistor. Here we are seeing an NMOS transistor. So we have a P substrate. It is lightly doped substrate. It is a P-type doped silicon substrate. And then we have polysilicon, that is the gate. So here you can see a metal contact on top of the polysilicon, and this terminal is called as gate. Below polysilicon there is a FOX layer, that is field oxide layer. It is generally silicon dioxide. It is an insulating layer, means it does not have any free charge carriers, or it does not conduct basically. And the thickness of this insulating layer is TOX, it's called as TOX. Then we have two other blocks, that is N plus region shown here. So one N plus region is connected to a metal contact and it is called as source terminal. The other N plus region is also connected to a metal contact and it is called as drain. The width of the source and drain is same and is equal to W. The width of the polysilicon, the length of the polysilicon is nothing but the length of the channel. And N plus here indicates highly doped N-type silicon. So now the P substrate is called as the bulk, and the bulk also needs a contact. We cannot directly connect the bulk to the metal, that is the P substrate to the metal, because it forms a Schottky diode. Hence we put a P plus region and then connect a metal region to avoid the Schottky diode, and this terminal is called as bulk. The designer can choose the length and width of the transistor. The designer cannot choose the thickness of the insulation layer TOX. It is fixed for a given technology, as well as the minimum length L minimum is also fixed. For example, 0.12 micrometer, which is equals to 120 nanometer technology. So the minimum length which the designer can choose for any transistor has to be 120 nanometers, and this is dependent on the technology. Symbol of MOS transistor. So this is the symbol of the MOS transistor. We have a gate which is shown here, and then we have drain, source, bulk. There is a diode which shows symbol which shows the diode direction. We know that this is the symbol of the diode, and this represents P region and this represents the N region. So here we can, this symbol represents that the bulk is the P region. So if the bulk is a P substrate, then it is an NMOS. So in NMOS, the symbol of an NMOS and the diode direction is like this. And there is dashed lines here, which shows that when the gate voltage or gate to source voltage is not applied, there is no current flow. This is the significance of the dashed line, that there is no current flow from the drain to source. The gap here between the gate and the dashed lines indicates the silicon dioxide layer, the FOX layer. So what kinds of lengths, widths and thicknesses are we going to see in this microelectronics chapter? As the title suggests, micro. The lengths are generally in the range of 0.5 micrometer and up to 32 nanometer, so it is very small. The thickness of the gate oxide is also very small, from 8 nanometers up to 2.3 nanometers. And the voltage levels which we are going to talk about, that is the supply voltages, are in the range of 5 volts until 1 volts. And once the supply voltage is less, the power dissipated is proportional to the power supply voltage square, and hence if you reduce the supply voltage by half, the power will reduce by 4 times.